it's Rachel, and I am here in a bunny suit at MIT Nano with Professor Vladimir Bulovich, who is going to show us around.
Well, it's a pleasure to have you here. Thanks for coming. Goal of this space is to enable anyone to build anything they wish.
Hey, it's still Rachel, but now I'm here at the Scientific American recording studio. As you just heard, today's episode is a little different from our standard format. We went all the way to Cambridge, Massachusetts to explore MIT's cutting-edge nanotechnology lab. You'll notice that our sound quality is a little lower than our usual standards, but that's just because we were surrounded by actual scientists doing actual science, along with all of their exhaust fans and fume hoods, of course. If you want to see all the cool stuff we're talking about during today's episode, including, of course, me in a full bunny suit, you can check out a video version over on our YouTube channel. You'll find a link to that in our show notes. Okay, let's dive back into our Surrounded by Big Science Machines immersion pod.
You were joking earlier that if you have allergies, this is the place to be. And I'm very allergic to dust mites, and I have noticed that I am breathing easier than normal. So.
Well, I'm glad you say that, because you're then a true proof of our numerical counting, because we do control for the dust particle count continually. We do speed up and slow down our purifying fans in order to make sure we are at a class 100 or better. And what that means is that in a cubic foot of air, there are 100 particles bigger than half a micron. Your hair is 75 microns wide. So half a micron is 150th the thickness of your hair. Anything bigger than that, we don't want to have any more than 100 of such particles in cubic foot.
Wow.
Out there, outside of this clean room,
yeah.
in a cubic foot of air, you would find 1 million such particles.
Wow.
So for every 10,000 particles, only one remains. And the way we do it is actually very simple. All you need to do is take all the air of this room and replace it every 15 seconds.
Oh.
That's
easy.
it.
Yeah.
Roughly speaking, about 250 exchanges of air per hour.
Tell me what it is that you guys do here that requires this level of cleanliness.
If you look at a dust particle, it's typically microns in size. 1 micron is 1,000 nanometers. If I'm to shape the nanoscale, I don't want to be confused by the size of the dust particle. From perspective of nanoscale discovery, a dust is like a boulder, and I need to make sure I avoid it. These suits and the way we clean the air and make it fresh and pleasant is indeed to avoid any of those dusts accidentally ending up in our experiments and hence confusing us.
And there's a lot of potential for accidental contamination because a ton of people work here. Could you tell me about, how many folks have experiments running here?
Absolutely. Well, we have in a whole facility about 1,500 people.
Wow.
Now, they're not here all on the same day, but they do come in and get their work done. Maybe a fifth of all of MIT's research depends on this facility touching a research element, from microelectronics to nanotechnology for medicine, to different ways of rethinking what would be next quantum computation look like. Any of these are really important elements of what we need to discover, but we need all of them to be explored at nanoscale to get that ultimate performance.
What is so important and exciting about doing research at the nanoscale?
Nanoscale is something you experience every day, but you don't often think of it that way. When you wake up in the morning and you make your cup of coffee and you smell it, I can ask you, why do you smell it? Well, something left the cup of coffee and reached your nose. Well, what did it leave the cup of coffee? It's a molecule. A molecule that's 1 nanometer in size carries the scent. The smaller it is, the more volatile it's going to be, and hence that is what's going to carry the scent. And if I'm smelling it, that means my nose is filled with nanoscale receptors. I'm designed to experience nanoscale.
Yeah.
And in the same way, when my eye gets excited by light, how big is the molecule behind my eye that collects that light? And the answer is 1 nanometer. If I go ahead and ask you what makes myself be able to feel when I touch my skin, well, it's opening and closing of the ion channels in my cell that make the pH of my cell slightly different. How big are those ion channels? Just a few nanometers in size. How wide is my DNA? 2 nanometers. When you take medicine, ibuprofen, how big is the molecule of ibuprofen? About 1 nanometer. How about vitamins A, B, C, and D? 1 to 2 nanometers. Whichever way you turn, whatever element of who we are you try to explore, you always recognize it's built down on a nanoscale. And it's only very recently we have the tools to truly see the nanoscale. And through that to infer how is it that all these physical processes happen And how do we help them if they might be hurt or they might be needing some sort of improvement? And through that, rediscover an entirely new way of thinking of what next set of technologies might be. Because once you see the nanoscale, you realize you missed a whole bunch of new things that could open up whole new vistas of opportunity.
You said that, it's only really recently that we've been able to explore the nanoscale scientifically. Could you give me a little bit more context for how new these tools are?
Sure. Well, the first time humanity saw atoms, actually took a picture of an atom and said, ooh, that looks really nice and round, was in 1980s, late 1980s. And you can imagine this instrument called scanning tunneling microscope was used. When they looked at that atom and saw it using this very sharp atomic scale tip, all of us were saying, wow, I want to do that. So maybe a decade into the mid-90s, we all had these instruments and we could start playing around and seeing the nanoscale. We were not really discovering anything new. We were just observing what we knew should be there, but never before saw. Much of our understanding of nanoscale prior to that moment was inference. It must be that they are atoms. It must be that the nanoscale is formed this way because of all these other phenomena we were observing. But seeing them, oh my gosh, did that change the way we thought? By early 2000s, we start learning how to move around atoms, quantum corrals. And by that, we can now shape nanoscale. Now, we're really doing is shaping like 5, 10, 20 atoms where we want them. And it might take a couple of days to shape those 20 atoms. But we were, for the first time, kind of exploring the opportunity of it. In parallel, we were developing technologies like organic LEDs, OLEDs, that use 1 nanometer size molecules, not as things we eat, but as things that can glow and can start acting like semiconductors. This blend between the nanoscale exploration through characterization toolsets like this and the advent of this whole new field of nanostructured electronics and photonics allowed us to say, this is real. There are so many opportunities here in the electronics world. In parallel, developments in medicine and the way that we can go ahead and detect various types of analytes from air, because we can smell particular molecules in the air by using carbon nanotubes and nanowires and little ligands that sit on the outside to snatch those molecules and change performance of those nanowires in some way. This was all new, and it's still very new, because it turns out that any discovery we make in a lab requires about 1 decade before that discovery can be in the hands of 1 million people. It's never been done in less time. Everything I described to you are ideas that have emerged in 2010, 2015, yesterday, by the scale of building new ideas forward. We are at the very, very dawn of the nano age, and it's thanks to the tools around us. These tools shape the nanoscale the way you want them, and then down in the basement of MIT Nano, we have the most exquisite imaging tools to be able to see the nanoscale. And then, on top of all of that, we have facilities that allow us to package the vision, the shape, into a technology that can then be given to others to hold in their hands and launch companies, or indeed enable society to truly benefit from these instantiations of nanoscale and then translations into real physical objects.
To give our listeners and viewers some sense of what actually goes on here, could you tell us about a few of the tools that help us study the nanoscale world?
There are some remarkable microscopes that allow us to see down to the atomic scale and below atoms. So aberration-corrected transmission electron microscope would be one of them. It sounds really cool, kind of a lot of words put together. Or cryogenic transmission electron microscopes. TEMs themselves are remarkable tools. They use electrons rather than photons to see the world around you. Whenever you take a picture, what you really are seeing is photons bouncing off an object coming to your camera, and your camera recording those photons that bounced off the object. And the smallest thing you can see with a photon depends on the wavelength of the photon. Blue light is like 400 nanometers, so maybe half of that is the smallest you can see with blue light. I need objects that have smaller wavelengths. Electrons have wavelengths just like photons. We don't think of it often that way, but we're okay talking about photons as being particles or waves. Electrons are also particles or waves. It's just their wavelengths are extremely small, angstroms in size, fractions of a nanometer. So let me use electrons as the things I'm going to shine onto my object, bounce them off, and collect them with an electron camera. That is what transmission electron microscopes do. They have an electron gun that shoots the electrons in collimated beam. It goes through the sample and collects whatever electrons can pass through with a camera. And you can hence see shadows of atoms. Electrons that did not arrive to the camera are the ones that got bounced away. But the ones that did are the ones that tell you what's the outskirts around the atoms. Incredibly powerful technique. And if you can keep those electrons very, very straight and keep your sample very, very still and correct numerically for some of the errors, you can get resolution that goes way below atomic scale. The smallest features we've seen easily, roughly, is so-called 60 picometers, and then we can get down to even to the scale of 30 picometers if needed. Or if you have a biological object that is squishy and wiggles around, you can't really think of seeing that at nanoscale. You can. It turns out that you can take that protein or cell element that you're trying to measure, cool it down so it stops wiggling, vitrify it. Vitrification is a process of cooling that's so fast that water never has a chance to solidify, and as a result doesn't burst the walls of whatever you're looking at. Once you have this frozen object, cryogenic frozen object, you put it inside a cryogenic transmission electron microscope. As a matter of fact, let's make 10,000 copies of this object, spread them, and then go ahead and shine the electrons onto them. Not very many electrons because they'll destroy the biology, but just a little bit. And you get a faint shadow image of those objects 10,000 times. Every object sits slightly differently in a different pose on that surface on which you're imaging. So now you have a 10,000 faint shadows.
Wow.
Spend a day numerically simulating what object could give you that particular shadows, and you can reconstruct a three-dimensional shape of a protein down to the scale of nanometers.
Wow.
And from that, learn how ibuprofen, maybe one day, how does it truly attach itself to the protein to help it? We need to see the nanoscale to understand how we are put together, because just very simplistically, DNA in every one of your cells happens to be exactly the same. Yet some of your cells choose to be brain cells, skin cells, heart cells. What gives? Well, it turns out the DNA sequence is extremely important, but also it's the twist in the DNA. Which kink do I have on what part of my DNA will make certain parts of it active and certain parts of it inactive?
Yeah.
I need to see that. And the only way to see that is by using these nanoscale investigations. And if I have that understanding, maybe I can cure diseases I could not cure before.
Yeah, very cool. And you also have fabrication tools here, right? What kinds of things are people building at the nanoscale?
Absolutely. You're surrounded by them. So the instruments around you allow you to shape nanoscale the way you wish. These are lithography tool sets. Notice the light is a little bit yellower here and it gets even yellower over there. And that's because all the light that we use to do lithography is typically in the blue end of the spectrum or the UV end of the spectrum. To avoid extraneous blue light messing us up, we take a white light bulb, we remove the blue color from it, and you're left with the amber light that you see around us.
Oh.
Hence, the only place you're going to see blue light or UV light is inside these tools. And the tools themselves will directly write onto your material. Now, how do they write? They have different ways. Basically, they either chisel away your particular object by shining extremely bright light of particular infrared color, or they shine blue light onto what's known as a photoresist that changes the chemical stability of a particular molecule that was exposed. And the exposed molecules can be, for example, washed away, leaving the unexposed ones on the wafer. Anywhere that has shown light now becomes a trench, and that trench exposes my sample, and that sample now, in the shape of a trench, can be patterned or shaped or such.
What kinds of materials and objects is that useful for?
So lithography, the way I described to you, can be used on any process material you wish. The most common you would find it, let's say, on silicon, because many people do use silicon. But so do variety of compound semiconductors, and so would be on two-dimensional materials that now allow us to rethink electronics. Or let's go beyond. How about superconducting materials? Materials that you need to cool down to show this state of matter known as superconductivity that allows us to make one day a very efficient quantum bit, qubit circuit. At this point, we have abilities to make small versions of those circuits, and we have perspectives on how to get to very larger ones. And when we do that, boy, will we have different kind of computation, more powerful, more potent for some problems that today are simply not solvable based on the energy or the slowness of the present digital electronics.
So our ability to really explore nanoscale is so new. We're learning new stuff all the time. What do you think is going to change because of research like this in the years ahead?
Well, you already are experiencing it continuously. We typically take our phone in our hand and then a few years later we replace it, expecting the next phone will be better. We don't really give a parade and a tremendous amount of ovation to the engineers who figured out how to squeeze in yet another set of pixels on your camera and make your color of your screen that much more visually appealing while having in it 17 different bands that they can communicate in different ways with Bluetooth or 5G, 6G and beyond. Each of those advancements that we hold in our hand every day is enabled because of yet another level of understanding of nanoscale that gave us the ability to make that technology that much more powerful. The things that are coming up, many. Molecular clocks, clocks that are almost as good as atomic clocks, losing only a second over a century, and yet compact enough and low energy enough to be present on any electronic device. That would allow us to synchronize technologies like never before, which would allow us to make communications even faster.
Yeah.
The way we think about solar technologies today is to ask, can I buy a large 1 by 2 meter panel filled with silicon wafers that weighs about 25 kilos, 50 pounds? That is yesterday's technology. I think of it very much as vacuum tubes of the solar era. What is the brand new transistor age of the solar era is going to be solar cells as thin as our fabric, wearable, light to deploy, very large in area because they are so light, consequently changing the paradigm of both manufacturing, rapid deployment, and hence decarbonization of the planet as we know it. There are opportunities just like that and many more that one can name. At this point, the future is built through the nanoscale. We are just at the beginning of the age of nano.
Super exciting. Well, thank you so much for chatting with us about nano and for showing us around. This place is really cool.
Thank you. Thank you for stopping by. I look forward to seeing you again.
Yes.
That's all for today's episode. Don't forget to check out the video version over on our YouTube channel. We'll be back with our weekly news roundup on Monday. Science Quickly is produced by me, Rachel Feltman, along with Fonda Mwangi, Kelso Harper, Naima Marcy, and Jeff Telvicio. Shayna Pozis and Aaron Shattuck fact-check our show. Our theme music was composed by Dominic Smith. Subscribe to Scientific American for more up-to-date and in-depth science news. For Scientific American, this is Rachel Feltman. Have a great weekend.